Physics is often described as the most complete science. It explains motion. It explains light. It explains gravity, electricity, atoms, stars, black holes. From the smallest particles to the largest structures in the universe, physics provides equations that predict reality with astonishing precision. And yet, there are cracks, small inconsistencies, unresolved measurements, observations that do not fit perfectly into our models. These are not mysteries in the dramatic sense. They are not violations of physics. They are something more unsettling. They are places where physics works, almost, but not completely. One of the largest anomalies in modern physics is invisible. Dark matter. When astronomers measure how galaxies rotate, they notice something strange. The outer edges of galaxies spin much faster than they should. According to Newtonian gravity, and even Einstein's relativity, there is not enough visible matter to hold them together at those speeds. If the equations are correct, galaxies should tear themselves apart. But they do not. Something unseen is holding them together. This something does not emit light. It does not reflect light. It does not absorb light. It reveals itself only through gravity. Dark matter is not a small correction. It makes up roughly 85% of the matter in the universe. We do not know what it is. For decades, physicists have built detectors deep underground, shielded from cosmic rays, hoping to capture a dark matter particle interacting with ordinary matter. So far, nothing definitive. Perhaps dark matter is made of exotic particles we have not yet discovered. Perhaps our understanding of gravity itself needs revision at cosmic scales. Either possibility would reshape physics. Then there is dark energy. If dark matter is strange, dark energy is stranger. In the late 1990s, astronomers studying distant supernovae discovered that the expansion of the universe is accelerating. Not slowing down, accelerating. Something is pushing space apart. This mysterious force has been labeled dark energy. It appears to make up about 68% of the total energy content of the universe. We do not know what it is. We do not know why it exists. We only know that without it, our equations do not match observations. The universe, it seems, is dominated by components we cannot directly observe or fully explain. Then there is the Hubble tension. When scientists measure how fast the universe is expanding, they use different methods. One method looks at distant supernovae. Another examines the cosmic microwave background, the afterglow of the Big Bang. Both methods are precise. Both are based on well-tested physics. But they do not agree. The expansion rate calculated from early universe data is slightly different from the rate measured in the nearby universe. The difference is small, a few percent. But in physics, small discrepancies matter. It may indicate a subtle measurement error, or it may hint at new physics beyond our current cosmological model. At the smallest scales, anomalies appear again. The muon is a particle similar to the electron, but heavier. According to the standard model of particle physics, we can calculate how the muon should behave in a magnetic field with extraordinary accuracy. In recent experiments, physicists measured the muon's magnetic moment. The result did not perfectly match predictions. The discrepancy is tiny, but it may suggest the presence of unknown particles influencing the measurement. Or it may vanish as calculations improve. The uncertainty remains. Another anomaly lies in neutrinos, ghostly particles that pass through matter almost without interaction. Neutrinos come in 3 flavors, and they can oscillate between these forms as they travel. This behavior was unexpected when first observed. It required modifying the standard model to include neutrino mass, something previously assumed to be zero. Even now, neutrinos behave in ways that are not fully understood. Some experiments hint at possible sterile neutrinos, hypothetical particles that interact even less than ordinary neutrinos. If confirmed, they would open an entirely new sector of physics. Then there is the proton radius puzzle. For decades, measurements of the proton size seemed consistent. But when scientists used a different method, Studying muonic hydrogen instead of regular hydrogen, they found a smaller radius. The difference was tiny. But again, small discrepancies challenge fundamental assumptions. Over time, improved measurements have reduced the gap. Yet the episode revealed how delicate our understanding of known particles can be. Gravity itself remains incomplete. Einstein's general relativity describes gravity as the curvature of spacetime. It has passed every experimental test so far. But it does not fit comfortably with quantum mechanics, the theory governing the smallest scales. When physicists attempt to unify these frameworks, infinities appear in the equations. Quantum gravity remains unsolved. Black holes deepen the mystery. According to relativity, information that falls into a black hole is lost forever. But quantum mechanics insists that information cannot be destroyed. This contradiction is known as the black hole information paradox. Recent theoretical work suggests that information may be encoded in subtle ways on the event horizon. But a complete resolution remains elusive. Even more unsettling are anomalies in the cosmic microwave background. Most of the radiation from the early universe is uniform, but certain regions, like the so-called cold spot, appear slightly different than expected. Is it random fluctuation, or a sign of something deeper? Some speculate about cosmic textures, large voids, or even interactions with other universes. The mainstream scientific community remains cautious. But the anomaly persists. Closer to Earth, smaller anomalies raise questions too. In the past, spacecraft such as Pioneer 10 and 11 appeared to experience slight deviations in trajectory, a tiny unexplained acceleration toward the Sun. For years, this Pioneer anomaly puzzled scientists. Eventually, it was largely explained as uneven heat radiation from the spacecraft itself. The anomaly faded. But the episode demonstrated how even small deviations can challenge confidence. There are also unexplained observations in condensed matter physics. Certain materials exhibit superconductivity at temperatures higher than expected. The mechanism behind high-temperature superconductors is still debated. Understanding it could revolutionize energy transmission. Yet decades after discovery, a complete theory remains out of reach. Physics is powerful, but it is not finished. Anomalies are not failures. They are invitations. Every major revolution in physics began with a discrepancy. The orbit of Mercury did not match Newton's predictions. Einstein explained it. The ultraviolet catastrophe contradicted classical physics. Quantum mechanics emerged. An anomaly is the universe whispering. Look closer. Most anomalies will eventually dissolve into improved measurements or refined calculations. But some may signal deeper shifts. The standard model of particle physics is extraordinarily successful. Yet it does not explain dark matter. It does not explain dark energy. It does not incorporate gravity. It is incomplete. And that incompleteness is not weakness. It is the frontier. Physics does not collapse because of anomalies. It grows. The laws of nature are not violated. They are expanded. And somewhere, hidden in tiny discrepancies and unexplained signals, may lie the next breakthrough, a theory that reshapes our understanding of space, time, matter, and reality itself. Until then, physics remains both triumphant and unfinished, precise, predictive, and still listening.